Newton's law of viscosity. This law is very important while we are studying the fluid dynamics. So let us see what is the law. To understand this law, we have taken one simple example. We have considered the two layers of the fluid, as you can see in the figure. The figure shows, see here, the figure shows these two layers of the fluid, and these two layers are y centimeter apart. That means the distance between the two layers is y meter. The area of the two layers is a meter square. Each layer area is a meter square. Fine. And the velocity of the top layer with respect to this bottom layer is u meter per second. Fine. There is some force we are applying, and that's why the fluid is moving. Fine. Again I am repeating. We have considered the two layers of the fluid. Each layer area a meter square. The distance between the two layers is y meter, and the velocity, or I can say top layer, moving parallel to the bottom layer with velocity u meter per second. And as it is moving, why moving? Because we are applying some force F. So according to Newton's law of viscosity, I can say that this force is directly proportional to velocity and area A, and inversely proportional to distance y. Again I am repeating, the force is directly proportional to velocity u and area A, and inversely proportional to distance y. So mathematically I can write that F is proportional to u A divided by y, because force is directly proportional to velocity and area and inversely proportional to distance. So F is directly proportional to UA upon Y. As here I am removing the proportionality sign, I have to introduce the proportionality constant, which is mu. So F is equals to mu UA upon Y, and this is mu is proportionality constant, which is known as viscosity. Fine. So I can write this equation as F by A. I have taken A on this side. So F by A is equals to mu u upon y. This F by A is replaced with tau, and tau is known as shear stress. So I can write this equation as tau is equals to mu u upon y. So tau is equals to mu du by dy. Why I am writing here du by dy? Because in this case the variable factor is only u and y. And what is that du by dy? Du by dy is nothing but velocity gradient, change in velocity with respect to distance. Fine. So that's why I have written it in the differential form, because that two parameters are varying. So tau is equals to mu du by dy, and this expression is known as Newton's law of viscosity. Fine. So this is Newton's law of viscosity, and it is very important for fluid dynamics. Now let us see another topic, Newtonian and non-Newtonian fluid. See the graph. Graph shows the tau versus du by dy. We know that tau is a shear stress and du by dy is velocity gradient. Now Newtonian and non-Newtonian fluid, we all know that Newtonian fluid are that fluid which obeys Newton's law of viscosity, and non-Newtonian fluids are those fluids which do not obey Newton's law of viscosity. You can easily identify from the graph. See here, Newtonian fluid shows the straight line. See here, this middle line shows Newtonian fluid. It obeys Newton's law of viscosity. So stress increases with respect to velocity gradient, so it is simple a straight line. Non-Newtonian fluid do not obey the Newton's law of viscosity, and in that there are two categories: time independent fluid and time dependent fluid. Let us see first time independent fluid. In this graph, there are three types of the time independent fluids are shown. See, Bingham, pseudoplastic and dilatant. All three lines are differ. See, this is the Bingham fluid, this is pseudoplastic and this is dilatant. Now what are that? Bingham fluid do not flow at all until threshold shear stress is attained. That means after some shear stress is attained, then only the fluid start to flow. That is Bingham fluid. So you can see in the graph there is some value tau 0, and after that the Bingham line appears. That shows that fluid do not flow at all until threshold shear stress is attained, and then it flows linearly. After threshold shear stress is attained, it flows linearly. And the examples of the Bingham fluid are toothpaste, jellies, etc. Fine. Next is the pseudoplastic. Pseudoplastic is what? The fluid viscosity decreases with increase in velocity gradient. Again I am repeating, viscosity of the fluid decreases with increase in velocity gradient. That fluid is known as pseudoplastic. And the example of pseudoplastic are rubber, latex, etc. And opposite to pseudoplastic, dilatant. You can see the graph also. Pseudoplastic and dilatant nature is completely opposite. What is dilatant fluid? Dilatant fluid are those fluids for which viscosity increases with increasing velocity gradient. That is known as dilatant fluid. And the example of dilatant fluid are starch in water, pulp in water. That are the examples of the dilatant. And Bingham plastic, pseudoplastic and dilatant are the category of time independent fluid, and it comes under the non-Newtonian fluid. Now if we talk about time dependent fluid, see, time dependent fluid are the relation between shear stress and time. You can see that in time dependent fluid there are two types of the fluid, thixotropic and rheopectic. See, the nature is completely opposite. This is rheopectic, this is thixotropic. It shows the relation between shear stress and time. From this I can say that thixotropic fluid are those fluids for which viscosity decreases with time, and rheopectic fluid are those fluids for which viscosity increases with time. The example of the thixotropic fluid is gelatin, paint, yogurt, cream, etc., for which viscosity decreases with time. And rheopectic fluid example is highly concentrated starch solutions, for which viscosity increases with time. Fine. So these are the time dependent fluid. Fine. So this is all about Newtonian fluid and non-Newtonian fluid, and the categories of all the type of fluid. Now let us see another important topic, which is Reynolds experiment. This is very important topic while we are dealing with fluid dynamics. When fluid is in motion, it is very important to know the type of the fluid. And to know the type of the fluid, you have to do the Reynolds experiment. So I can say that from Reynolds experiment, we can know the type of the fluid. So Reynolds experiment is used to find out the type of the flow. There are mainly two types of the flow, laminar flow and turbulent flow. This Reynolds experiment was first conducted by the scientist Reynolds, and that's why it named as Reynolds experiment. And at the end of the experiment, he found out a one dimensionless number and he gave the number name as Reynolds number, that we will see in this session. See the setup of the experiment. See, this is the glass tank. In this there is the glass tube and this is a dye tank. In dye tank we fill a colored dye water. Fine. So this is glass tube, this is dye tank. With the help of this pinch valve, the flow rate of the dye water we can regulate. Now the glass tube with flared entrance, see here, this is the flared entrance, this glass tube with flared entrance immersed in a glass wall constant head filled tank which is filled with water. By introducing a water soluble dye into the flow of water, from this with the help of pinch valve we can introduce the dye water which is mixed with the water in a glass tube. So by introducing a water soluble dye into flow of water, the nature of the flow could be observed. It is made up of glass, so you can easily visible from the outside that how the colored dye water entered into the glass tube and what is the nature of that water. At low flow rate, filament of the colored water flow in a straight line without mixing. When the flow rate is low, you can easily observe that at low flow rate there is a simple straight line of the colored water. And as you are increasing the flow rate, the nature of the colored water which is going into the glass tube is changing. Let us see how it changes. You can easily understand from the next figure. See here. First, as the low flow rate, you can see this straight line of the colored water. As the flow rate increasing, it moves like this. Again the flow rate increasing, it moves like this. So these are the different types of the flow according to the type of the flow rate. So the water was flowing in a parallel streams which do not interfere with each other is known as streamline or laminar flow. The first one. Fine. At low flow rate, the water was flowing in a parallel streams which do not interfere with each other, known as streamline or laminar flow. As the flow rate increased, the velocity called critical velocity was reached and color water becomes wavy. At low flow rate, it flows like in a straight line and then it becomes somewhat wavy. So as the flow rate increased, velocity called critical velocity was reached and colored water becomes wavy, which results into complete mixing and it is known as turbulent flow. Fine. And between these two types, there is a transition region where oscillation in flow was unstable and quickly disappeared. That is the transition region. So you can easily understand from here. See, in a straight line it is known as laminar flow, somewhat wavy is known as transition region, and when it moves like this, it is known as turbulent flow. So mainly there are two types, laminar flow and turbulent flow. So according to this experiment, from this experiment, Reynolds find out a dimensionless number which is known as Reynolds number. Now what is that Reynolds number? Reynolds found that the critical velocity for the transition from laminar to turbulent flow depends on the diameter of the pipe, velocity of the flowing fluid, density and viscosity of the fluid. So Reynolds found out that these change in velocity due to change in this flow nature depends on these four parameters: diameter, velocity, viscosity and density. And from that, he made a dimensionless number. He grouped these all four variables into one dimensionless group, and that group named as Reynolds number. See, he grouped these 4 variables into one dimensionless group known as Reynolds number, and it is denoted as NRE. So NRE is equals to du rho by mu, and it is known as Reynolds number. And after so many experiments, it is found that when NRE value is less than 2100, it is known as laminar flow. When NRE is greater than 4000, it is known as turbulent flow. And when NRE is between 2100 and 4000, it is known as transition region. So according to Reynolds experiment, Reynold has derived one dimensionless group which is known as Reynolds number, and with the help of this Reynolds number, we can find out the type of the flow. Either it is laminar flow or turbulent. So that's all about today's session. I hope this is clear to all. Thank you.